In our last lecture, we spoke about strain tensor, and in stress tensor, we have discussed about the principal values of stresses. We also spoke about principal values of strain, and we also talked about the deviatoric stress tensor. So, deviatoric stress tensor is the conventional stress tensor minus the mean stress, right? And our stress tensor is a symmetric tensor, and also strain tensor is a symmetric one, because we took the antisymmetric out of it, and in stress we don't have antisymmetric part there. So what do we mean by symmetric tensor is that the transpose of this will be equal to the original tensor. So sigma ij will be equal to sigma ji, and so will be with the case with epsilon, right? So in matrix notation it will be sigma is equal to sigma transpose. So this is what we mean by symmetric tensor, right? So although this stress, which is the deviatoric stress, although this does not have any shear component in it, a normal component in it, because we have seen in our assignment that all the components, even the diagonal one, are shear stresses. Okay, so even if it is not like conventional stress tensor, it is still a symmetric tensor. Okay, because by doing this operation we are only changing the diagonal values. We are not changing any value which is non-diagonal, right? So we are not changing any value when I is not equal to j. We are only changing when I is equal to j, and when you take a transpose of that, so the diagonal elements do not change, they remain where they are, and the upper triangle elements, they go to the lower triangle, and lower triangle elements go to the upper triangle. That's what happens in a transpose, right? So therefore this tensor is also a symmetric tensor. So now, because it is a tensor, although it does not have normal stresses, it will still follow the property of a tensor. That means it will still have eigenvalues. So we can operate on this deviatoric stress as we did to find out the principal stresses, and by doing this we operate on deviatoric stress as we did to find the principal stress values. And the solution of this will generate a cubic equation again, and the coefficients we will call this time with j. So this will be j1 lambda square plus j2 lambda minus j3 equals 0, right? So j1 you have already tried in your assignment in your attempt to prove that this tensor does not have any normal stress. You tried by calculating the first invariant of this tensor, and you know, because you did it, that it was 0, right? So j1 is invariant and the value is 0. j2 is a combination of, so j2 is actually the principal minors of this stress tensor. Okay, so we can write j2 as 1 by 6 of sigma 1 1 minus sigma 2 2 whole square, and plus sigma 2 2 minus sigma 3 3 whole square, plus sigma 3 3 minus sigma 1 1 whole square, plus 6 into sigma 1 2 square plus sigma 2 3 square plus sigma 1 3 square. Okay, so this is what you will get. You know how to get it. You know how to get the principal minors of any 3 by 3 matrix. So this is what is the value of J2, and so it's a combination of shear stresses, right? And J3 will be the determinant of sigma d, right? And determinant of sigma d is actually, determinant of any matrix is actually the multiplication of the pivot points. So you just, if you make the lower triangle 0 somehow, then you just have to multiply the diagonal elements, and that will be the value of the determinant. So in this case, if we know the principal values, let's call those sigma d1 2 3, then the value of determinant will be sigma d1 into sigma d2 into sigma d3, and that's it. So that is the value of this, right? So this we know now, and this was similar to the principal values of strain tensor and stress tensor. And now we come to the elastic stress strain relationship. Okay, so we talk about elasticity. So you know about Hooke's law. The simple one is sigma is equal to elastic modulus into epsilon. Sigma is the stress, this is elastic modulus, this is strain. Okay, so this is known to us, but as I said, if you pull a tensile specimen, for example, and so imagine it to be a rectangular specimen which looks like this, and we are just talking about the relevant details, so we are not going into the experimental design of the specimen and how it should be. We are just talking about the part which is relevant. So this is a rectangular parallelopipe, and we somehow pull this by applying a tensile force on that cross section, and we fix this cross section. Okay, so when we do that, we know that there will be a change in, there will be an elongation, right? So this box will elongate, and it will contract in the other two dimension. So in this dimension it will contract, and in this dimension, so in this dimension and this dimension it will contract. Okay, it will only elongate along. So let me make the axis. So this is x1, and the upper one is x2, and this is x3 along the thickness. So in x2 direction it is elongating. So in x1 and x3 it will contract, right? So if we have epsilon y in y direction, and this is tensile, so we keep that positive, right? Or we can call it epsilon 2 2. So because of contraction, epsilon 1 1 will be equal to epsilon 3 3, which will be equal to the Poisson's ratio into epsilon 2 2, because we know this, that this contraction is related to the diametrical contraction. You have read it in your school days, and that's how you calculate Poisson's ratio. Okay, so we know that in elasticity the volume is not constant, and the relationship is given by the Poisson's ratio, and so this will be the relationship between strains in the other directions, right? So now we can do this for all three dimensions. So we have done it for when we apply stress in the x2 direction. So we can write it down, right? So if we have stress in, so stress is in sigma 2 2 direction, so we get so this is x1 direction, this is x2 direction, this is x3 direction. So in x1 direction we have epsilon 1 1, which is equal to minus epsilon 2 2, right? Is that is correct, right? So we get minus mu into epsilon 2 2. In 3 3 also we get mu into minus mu into epsilon 2 2, and here we get epsilon 2 2. Okay. Yes. Now similarly, if you just change your coordinate system so that so now just imagine that this is x2. Okay, so let me write that differently. So now we are rotating this, so this becomes x1, this becomes x3, and this becomes x2. Okay, so what happens? So now our stress is in the direction of x1, so we have sigma 1 1, right? Sigma 1 1, so therefore the strain will be epsilon 1 1. In other direction we will have mu into epsilon 1 1, mu into epsilon 1 1. Similarly, if we do this in the third direction, we will have epsilon 3 3, then minus mu into epsilon 3 3, and here we will have minus mu into epsilon 3 3 again. Okay, and so now we can change this further. So we can change this to the stress form, right? So this is actually my epsilon 1 in this case, which is equal, so epsilon 1 is equal to minus mu into epsilon 2 2, right? And epsilon 1 1 here, if we follow this relationship, so epsilon 1 1 we can write will be equal to sigma 1 1 divided by E, right? So therefore, sorry, epsilon 2 2, epsilon 2 2. Okay, and epsilon 1 1 is equal to epsilon 3 3 is equal to minus mu into epsilon 2 2, which will be equal to minus mu sigma 2 2 by E, right? So we will apply this conversion in this case. So this will be what? So this was for when our stress was applied in the sigma 2 2 direction. Okay, so we can write it. So this was minus mu into epsilon 2 2, so the first term will be, if we change it to stress, it will be mu into sigma 2 2 by E, right? Epsilon 2 2 will be sigma 2 2 by E, and this, when I'm writing in x1 direction, this is actually epsilon 1 1, right? This is actually epsilon 2 2. So let me just break it. Okay, and so we are changing here. Okay, so this is epsilon 2 2. Whenever we write in x2 direction, it is epsilon 2 2, and this is epsilon 3 3 equals to minus mu into epsilon 2 2, which will be minus mu into sigma 2 2 by E, right? So now we will do it for all cases. So epsilon 1 1 will be equal to, it is equal to epsilon 1 1, and in this case we have changed the things. So stress was in x1 direction, so this will become sigma 1 1 by E, and this will become minus mu into sigma 1 1 by E. This will become minus mu into sigma 1 1 by E. Okay, and again this is epsilon 3 3, epsilon 2 2, epsilon 1 1. Now for the third case, it will be minus mu into sigma 3 3 by E, and minus mu into sigma 3 3 by E, and this will be sigma 3 3 by E. Okay, and now if so, because we are talking about small strains and we are talking about elastic deformation, we can assume that the normal stresses in one direction are um, not not influencing the stresses in other direction. We also assume that shear stresses are not contributing to the normal stresses, and these are the assumptions which we make in order to apply the superposition. So now we can superimpose that what will be the complete epsilon 1 1 if we have stresses in all three directions. So then we will just sum this. So epsilon 1 1 will be equal to, what happens if you sum all these three? It will be sigma 1 1 by E minus mu by E sigma 2 2 plus sigma 3 3. So sigma 2 2 plus sigma 3 3. Okay. So this will be the relationship between epsilon 1 1 and other stresses, all three stresses. Okay. Similarly, you can find for epsilon 2 2 from this and epsilon 3 3 from this. Okay. So for epsilon 2 2 it will be sigma 2 2 by E minus mu by E into epsilon 1, sorry, sigma 1 1 plus sigma 3 3. And here it will be sigma 3 3 by E minus mu by E sigma 1 1 plus sigma 2 2. Okay. So this is my relationship between strain and stresses. Okay. So let me go to the next page. So in general, we can write the relation between strain and stresses as epsilon ij is equal to 1 plus mu by E sigma ij minus mu by E sigma kk delta ij. Okay, right? And I can write it for you so that it becomes simple. So I will not expand this side, but this can be written like this: sigma 1 1 sigma 2 2 sigma 3 3 sigma 2 1 sigma 2 3, and just write all the components. Minus mu by E, and this is just identity tensor. So this will be sigma 1 1 sigma 2 2 sigma 3 3. So this is it. Okay, and if you do this, you will get your strain tensor. So 9 components of that. So this is what we mean by these symbols. Okay. So now if you can also find out the relation of stresses. So how to calculate stresses from strains. Okay. So we know that you can find this, that sigma x plus sigma y plus sigma z, or let me write it sigma 1 1 plus sigma 2 2 plus sigma 3 3 is equal to E by 1 minus 2 mu into epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. This you can find out by finding the expression for epsilon 1 1 2 2 and 3 3 and just sum all three equations, and you will find this relationship. Okay, and this relationship actually tells you about some other things which we will explain later, but right now we want to find out how to get stresses from strains. Okay, so now let me write the expression for, let's say, sigma 1 1, sorry, epsilon 1 1. So if we have to find out epsilon 1 1 from that, it will be 1 plus mu by E sigma 1 1 minus mu by E sigma 1 1 sigma 2 2 plus sigma 3 3. Okay, this is what you get, right? Right. So now we can replace this term with this. Okay, so what happens if we do that? And then we take this term on this side. So we take sigma 1 1 term on this side, and we take epsilon term. So you take this term that side. So you take this term on that side. So you will have sigma 1 1 term on the right hand side, and then just flip it. So I can write 1 plus mu by E sigma 1 1 equals epsilon 1 1 minus, sorry, this will become plus mu by E, and this now we are replacing with that, so it will become E divided by 1 minus 2 mu. Okay, mu is Poisson's ratio. 2 mu and epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. Okay, so sigma 1 1 is equal to E by 1 plus mu epsilon 1 1, and E is cancelled, right? So this becomes mu divided by 1 minus 2 mu, and then you have 1 plus mu coming from this side. Sorry, you will have E divided by 1 plus mu, right? So this will go up, this will go down, and then so summation of epsilon II. Okay, so this is my expression for stresses if I have to calculate from strain. So let me write the generalized forms. It will be sigma ij is equal to E divided by 1 plus mu epsilon ij, right? E divided by 1 plus mu epsilon ij plus mu into E divided by 1 minus 2 mu into 1 plus mu, and so that is that, and this becomes epsilon kk delta ij, right? So this is my expression to calculate stresses from strain, and this was strain from stress. Okay, so this term here is, so the term mu E divided by 1 plus mu into 1 minus 2 mu is called lambda, denoted by lambda, and its Lami's constant. Okay, so now sometimes we can still make it further contracted instead of writing 9 components. So for example, in plane stress we know that we don't have stresses in one direction, right? And so we will have stresses like, we will have stresses sigma 1 1 and sigma 2 2. Sigma 3 3 is 0, and all that, so all this is 0. Okay, all this is 0 in plane stress, right? So we have only 4 components, and because of symmetry this one is equal to that one, so we have 1 2 and 3 components, so which are sigma 1 2, sigma 1 1, sigma 2 2, and sigma 1 2. Okay, so we can write the relationship between stress and strain in the matrix form. So we can write sigma 1 1, sigma 2 2, and sigma 1 2 equals E divided by 1 plus mu into 1 minus 2 mu, and then you make a matrix 1 minus mu 0. Okay, and then 1 minus mu again, then 0.5 minus mu, and then mu here, and then 0 0 0 and then you write epsilon. So this is another, so epsilon 1 1, epsilon 2 2, and epsilon, sorry, this will be gamma 1 2. Okay, so you know gamma 1 2 is equal to 2 of epsilon. So this is engineering shear strain, which we spoke in our last lecture, in the lecture of strain tensor, right? So this is the relationship between stress and strain in plane stress. This is one way of plane stress, sorry, one way of writing it. In plane strain, you just have 4 components here. So you have sigma 1 1, sigma 2 2, sigma 3 3, and sigma 1 2. Okay, so because strain in third direction will be 0, so sigma 2 3 and sigma 1 3 will also be coming out to be 0, right? No, so that was completely wrong what I said. When we have, so this was for plane stress, so this is right. For plane strain, we will have strain matrix component 0. Okay, so we will have only 3 values of strain. So we'll have epsilon 1 1, epsilon 2 2, and epsilon 1 2. Okay, and in that case we will have stresses which will look longer. So we will have sigma 1 1, sigma 2 2, and sigma 3 3. Then we will have sigma 2 3, we'll have sigma 1 3, and sigma 1 2. Okay, so 3 normal, 3 shear because of symmetry, right? So we have actually the whole stress tensor here. Okay, so we have, so this is equal to sigma 3 2, this is equal to sigma 3 1, this is equal to sigma 2 1. So these resembles actually 6 components plus 3 9. So all are there. This will be equal to again E divided by 1 plus mu into 1 minus 2 mu, and now I have to write a big matrix. So you know what will be there in this side, in this strain. So you will have only these 3 components, and rest corresponding to that will be 0. Okay, so now we will have 1 minus mu, 1 minus mu, then 1 minus mu, then 1 minus 2 mu, 1 minus 2 mu, and 1 minus 2 mu. Okay, and here we will have mu mu mu, and 2 more here, and all other will be 0. So all other components are 0. Okay, so this will be the matrix, and then you will have the strain matrix where only these 3 terms will be there. So this will be the condition for plane strain. Okay, this is one way of writing. Instead of writing 9 components, you can write only 6 components, because you know that 3 components are equal to other 3 because of symmetry. Okay, and by describing plane stress and plane strain, you are actually taking care of the all possibilities. So you can only have 2 situations, either plane strain condition or plane stress condition. Everything fall into these 2 categories, and you know the relationship. So this may look a little complicated, but when you formulate something in matrix form, or if you have to write a program in a matrix form, then it becomes very handy. If you are writing something in in array form, then this form becomes very handy. But so both writing ways have their own advantage. Okay, so this was the relation between stress and strain, and strain and stress. So if you have to calculate stresses from strain, you use this one. If you have to calculate strains from stress, you use this one. So let us talk about, we have in our one of the tutorials we talked about the energy consumed during deformation, right? So that we call strain energy. strain energy. Okay, and there is a place to fill, which we will fill after our discussion. Okay, so what we said in our tutorial is that now imagine that my material is going to deform only elastically. Okay, so this is my strain and this is my stress axis, and it's a linear relationship, so it will look like this, right? And then at some point of time it will just break. The sample will break into two pieces, and then the stress will be zero because machine will not feel anything, so it will just be zero. So that point I don't have to plot, but we know that it ends here, right? It ends here. So the area under this curve, because it is linear, it's a line, right? It breaks at a 90 degree. This is 90 degree, right? So it's very simple. What is the area under this curve? So this point is, let's say, epsilon failure, right? And this point is sigma failure. So the area is half into sigma failure into epsilon failure. This is the area under this curve, and this much amount of energy has been consumed by the specimen. So a specimen has taken this much amount of energy you have supplied to the to the specimen. So now suppose this was our piece of a specimen, right? And you applied a force of P, and it had an elongation of delta. Okay, so my energy will be force into displacement, right? And if you actually plot, instead of stress strain diagram, if you plot force versus displacement, right? So again this will be a straight line, right? And the area under this curve will be half into P into delta, right? And from this also you can come back there, but there will be a difference in these two. So force, if I have to write, I can write force as stress into area of this specimen, and delta will be strain into length, right? So epsilon into whatever is the is this length. So epsilon be delta by L, right? And the total deformation what you had was, so actually, so I have to write delta, and epsilon is equal to delta L by L. So I had an extension of delta divided by L. So epsilon, so if I have to write delta, it will be epsilon into L, right? So this is equal to half into stress into strain into area into length, and this is equal to volume. So what is this then? If this is the energy, so the energy consumed, let me write energy consumed E is equal to half sigma epsilon into volume, then U is equal to E by volume, right? So this is energy per unit volume, this one, okay? And this energy per unit volume is called strain energy density, okay? So this is called strain energy density. And now you can actually write U at any point of time is equal to sigma ij into epsilon ij, right? And if you take the derivative of this with respect to any strain component, epsilon ij, put it any strain component, what should you get? This is energy, right? And you know that the derivative of energy with respect to distance is a force, right? So if you take so you know that any force comes because of the change in energy, because of energy gradient, right? So force is the first derivative of energy with respect to the space, right? Spatial direction. Now here the only difference is I have strain. So the derivative of energy with respect to strain should be stress. Okay, so it doesn't matter, energy you will get only one component, only one value, because it's a scalar value. But if you do the first derivative with respect to any component, you will always get sigma ij. Okay, which will be equal to always Lami's constant into volumetric strain plus 2 into shear modulus into epsilon ij. Okay, so this is always true, and this you can check. Okay, this you can try and check. Now I stopped the discussion in the previous page when we spoke about the relationship between summation of sigma 1 1 sigma 2 2 sigma 3 3. So what was the relation between sigma 1 1 plus sigma 2 2 plus sigma 3 3 3 3 equals to some multiplier into epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. And if you remember, this multiplier was E by 1 minus 2 mu, right? So what is this? This is hydrostatic stress. What is this? This is 3 into hydrostatic stress. This is 3 into volumetric. No, this is volumetric stress. There is no 3 here. Okay. So this becomes equal to E by 1 minus 2 mu, right? So this is volumetric strain, okay, and this is hydrostatic stress. Okay, so what is the relation between hydrostatic stress and volumetric strain? The relation between hydrostatic stress and volumetric strain is called bulk modulus, right? Volumetric strain is bulk modulus. So now you can replace sigma h with, so here we have delta, right? So sigma h with k delta. So we will have 3 into k delta equal to E by 1 minus 2 mu into delta, which cancels out, and now we have a relationship between k bulk modulus and elastic modulus, which is this 3 into 1 minus 2 mu. Now we have to talk about a tensor which is a little bigger than a stress and strain. So when we write sigma is equal to E into epsilon, and we discussed all the relationships possible, and you remember we also wrote that big matrix with 6 components of stress, and then you had a big matrix and then 6 components of strains, right? So in order to get 6 cross 1 matrix out of multiplication of that big matrix into the other matrix of 6 cross 1, you have to have a 6 cross 6 matrix, right? And that 6 cross 6 matrix will have 36 components. But in that case, we applied a contraction. Instead of 9 components, we only dealt with 6 components in a column vector, right? So maybe you know where we are going with this. So this is not one value, this is not single value. So therefore, this constant which we call elastic modulus, it cannot be just one value. Okay, so the complicated part is sigma is a 3 by 3 matrix. That means it has 9 component of stresses. We have 9 component of strains. So this is also a tensor, and this is a 4th rank tensor. Stresses and strains are 2nd rank tensor. Okay, so this fourth rank tensor, because we have, so first rank tensor is vector, so we have 3 to the power 1 components, which is 3. When we go to second rank tensor, we have 9 components. When we go to fourth rank tensor, we have 81 components. So we will have 81 components. So we will have to write a matrix of 81 components in that. Okay. So in tensorial notification, we can write that as sigma ij is equal to C I j k l epsilon k l. Okay, and this is called compliance tensor. You can also write it other way around, is equal to S I j k l sigma k l, and this is called stiffness tensor. So stiffness tensor is the inverse of compliance tensor. Okay, so now how do we deal with this fourth rank tensor? How can we, so now we know that instead of one value of elastic modulus, we should have 81 values of elastic modulus, right? So is there a possible way to make it a little simpler? The answer is yes. We can make this, we can reduce the number of components in this one, and we have seen this in our last page, that we don't really need so many values to describe the relationship between a stress and a strain, right? Because we have discussed that strain epsilon ij is equal to 1 plus mu by E sigma ij minus mu by E into sigma kk delta ij, right? So we actually don't have 81 components here, but still we are able to describe the relation between stress, strain and stress for all 9 components, right? So this is valid for all values of I and j. So that means for all 9 components. So how are we doing this? How is this done? So we will try to explain that a little bit. So first of all, we know that stress tensor is a symmetric tensor. Okay, so we apply this symmetry. So we know that sigma ij is equal to sigma ji, right? So sigma ij, so we can write it, sorry, instead of that we write epsilon ij, and we deal with only stiffness tensor, which will be true for compliance tensor also. So epsilon ij we can write as Sij kl sigma kl, right? And we can also write epsilon ij is equal to Sij lk sigma lk, and we can write this because we know that sigma kl is equal to sigma lk because of the symmetry of stress tensor, right? So if this is true, then this must be equal to this, right? Therefore Sij kl should be equal to, must be equal to Sij lk, right? So this is true. Now similarly, we know that strain is also a symmetric tensor. Symmetric tensor, right? So now we can write epsilon ij is equal to Sij kl sigma kl, right? And because of symmetry, epsilon ij should be equal to epsilon ji, which will be equal to Sji kl sigma kl, right? So because of symmetry these are equal, therefore this must be equal to that. So we have Sijkl equal to Sjikl. Okay, so this is also true. Now we know that there are 81 components in our, then S1121, S1122, S1123, and then we will have, so 1 2 3 4 5 6, and we need 3 more, right? So and the last 3 component will be S1131, S1132, and S1133. Okay, so you see this will not be affected because S1111 will be equal to, if you change this to this or vice versa, this to this, vice versa, this is not getting affected because of symmetry. Okay, this is getting affected only by one symmetry. Okay, so that means by the symmetry of KL. This will not be affected by this one, and similarly for that one. But this, what about this one, and what about this one? So these two terms will also be not affected by both of these. Okay, so both of these symmetry, apart from affecting these 9 components, it will also not affect these 2 components, right? And we can try to do this in one of the tutorials and try to check that how many components will be affected by the symmetry or not, and the result will be, because of these symmetries we can reduce 81 component to 36 components. Okay, so we can do that, but can we further reduce this, because we still don't have 36 components here. Okay, dealt with strain energy density, which was U, right? And we know that when we take the derivative of this, we get stress, right? So now, but before doing this operation, before utilizing this, we have to have a contraction of notification. So instead of writing Sijkl, now we can apply a contraction. So what we say now, that instead of writing 4, we write only 2 indexes for this component. So let me open it up for sigma 11. So for sigma 11 we can write C11, this is compliance tensor, epsilon 11 plus C12 epsilon 22 plus C13 epsilon 33 plus C14 epsilon 23 into 2 we will have, plus C15 2 into epsilon 13 plus C16 2 into epsilon. So we have 2 3 1 3, and then we'll have 1 2. Okay, so what we are doing is, instead of writing C1111 C1112, we are just taking the row number and column number. So whatever column it is for, so this is row number 1, so the first index of this compliance tensor we are taking 1 always. So 1 1 1 1 1 1. Okay, and whatever is the column number we write that. So column number 1 C11, column number 2 C12, column number 3 C13, right? And because we have only 36 components now, so we don't have to write 9 by 9, we have to write 6 by 6 matrix, right? So we'll only go till column 6 and row 6, and this is what I have shown you in our starting of the lecture, where we dealt with 6 by 6 matrix and the stress vector, if you remember the condition for our plane strain. So sigma 2 2, sigma 3 3, sigma 2 3, sigma 3 1 or 1 3, and sigma 1 2. Okay, so now we are changing our dimensions from 9 to 9, 3 cross 3 to 6 cross 1. This is 6 cross 6, and then strain of 6 cross 1 again. Okay, so now we write like this, and then we can utilize this information here. The information here is like, so you have the expression for sigma 1 1 now, right? So now if I do the first derivative of sigma 1 1, okay, so we know that if we do the first derivative of energy, let's say del u with respect to epsilon 1 1, we will get sigma 1 1, right? And we have the expression for sigma 1 1. So what will happen if I do the double derivative of this with respect to epsilon 2 2? So you will have only this term, all other terms will be 0, right? So this will be equal to epsilon 2 2, right? So sorry, not epsilon 2 2, C12, right? And then if you do the first derivative with respect to epsilon 2 2, what will you get? Sigma 2 2. Okay, and sigma 2 2, now you can write the expression for that one similar to this one, and if you do double derivative of that, del epsilon 2 2 del epsilon with respect to 1 1, what will you get? You will get C21, because this will be second row, so everything will start with 2, right? And because you will be doing the second derivative with respect to epsilon 1, so this will be C21 epsilon 1 1. So you are doing second differential with respect to epsilon 1 1, so only this term will remain and all other terms will become 0. So this will be equal to C21, and you know that these two are same, therefore C12 has to be equal to C21, right? So now we can apply this symmetry again. Okay, and because this is a 6 by 6 matrix, okay, this is a 6 by 6 matrix, we have 6 1 2 3 4 5 6 components along the diagonal, which will not be affected because of this symmetry, right? So C12 is equal to C21, so all this thing will be affected only along this axis of the diagonal elements. So these 6 are not going to get affected. How many are there? So we have total 36 minus 6, so we have 15 on the upper side, 15 on the lower side, right? So we have 15 here and we have 15 here, so 30 plus 6, 36, right? But because these 15 are equal to that 15, so we have only 15 component which are independent plus this 6 component. So we have 15 plus 6 is equal to 21 independent components. Okay, so after doing all this, we arrived from 81 to 21, but still 21 is much higher. And after this, we apply the symmetry of the cubic crystals. So we now really apply the symmetry of the crystalline structure, and different crystal structures have different levels of symmetry. So when we talk about cubic crystals, we can actually reduce this 21 to 3, only 3 independent components. And you have seen this because when we wrote that relationship between of plane strain condition, so you saw that all the components there where actually 1 minus mu, 1 minus mu, 1 minus mu, 1 minus 2 mu, 1 minus 2 mu, 1 minus 2 mu. Then we had mu, mu, mu. Rest of the things were 0. And we had Lami's constant here. Lami's constant divided by mu. Right? So this was our C matrix for plane strain condition. And so you see Lami's constant has only elastic modulus E, then we have Poisson's ratio mu, and then we have shear modulus G. But G is also can be described as a combination of E and mu. So basically we have only two independent constants for a cubic crystal, right? Yes, so we actually have only two constants, two independent constants, and this is true for an isotropic crystal. So for an isotropic condition, so when we talk about monoclinic type of crystal or triclinic or tetrahedrons, so for those kind of crystals you will have elastic modulus different in different direction. So this was all. Lattice parameter is a property of the crystal of certain element. So for example, iron will have a lattice parameter different from chromium or tungsten or molybdenum or any other element, even if they are forming VCC structure. Okay, so how is this decided? This is decided by the atomic size. Okay, atomic size. So therefore the equilibrium between two atoms is achieved at a fixed distance. It's not possible for these two atoms to be in complete contact with each other. Okay, because if they come very close to each other, then the protons in the nucleus will start repelling, right? Because they both have same charges, so they can't really be together, and they also cannot be, so they have their own attraction but they cannot come very closer, and therefore they find their own lattice parameter. So they find their own space, their distance with each other, and this is what describes the amount. So if you are trying to extend these two atoms by applying stress, okay, so let's say that this is my x1 direction and this is my x2 direction. So in x2 so you are applying sigma 2 so and let's say the strain is epsilon 2 because of that. So this will have a relationship which can be given by certain compliance ijkl some value. So that is some value, so that is C epsilon 2. So this C describes the elasticity in this direction because of this arrangement of atoms, right? Now if the distance between these two atoms along x3 direction is also A, then you will have same elastic modulus working here, right? So you will have same elastic modulus, same bond strength, because all the atoms are same and the lattice parameter is same. Okay, so this will also be same. So C in 2 direction, so C22 will be equal to C33, right? So that will be same. But what about if you try to apply a force in this, a stress in this direction? So here you don't, so this distance is not a, this is root 2a, right? This is root 2a. So in this case the value of c will not be same. Okay, so in the shear direction, this will be a shear direction if we have this coordinate system. Similarly, if you have a crystal structure which is not orthogonal to each other, okay, so if let's say that it looks like this, okay, so on this plane, so let's say that in this is x1, this is x2, and this is x3. Okay, so on x1 x2 this is 90 degree, so here it is orthogonal, but here on the x3 direction it has a tilt, it's not 90 degrees, so 90 will be like this, but it has a tilt. Okay, so what will happen, this is a, and this is also a, right, and this is also a, but because of tilt the stress applied here will not be normal stress, it will be a shear stress, right? So if you apply a stress in this direction in x sigma 33, then sigma 33 will be actually working not along the atoms in this direction. So if you take this as the axis of atoms, this as the axis of atoms, the stress is actually working at certain angle. Okay, and this sigma 33 therefore along the axis of atoms will have a normal component as well as a shear component, right? So the stress which will be parallel to this direction, so let's say this is theta, so this will be 90 minus theta. Okay, so the stress which will be along the axis of this will be sigma 33 cos 90 minus theta, so sigma 33 sin theta. So along this direction it will be sigma 33 sin theta, and this sigma 33 sin theta now is at a distance of a. So if this is sigma 22, right? So in this case sigma 22 let's say has a relationship of c to 2 epsilon 22, but sigma 33 sin theta will have whatever is the constant in that direction, so we cannot call it 3, but so let us call that dash, and the strain in that direction will also be epsilon 33, but the strain is in that direction, so that will be in 3 direction will be again epsilon 33 cos sin theta, right, sin theta. So now this is not equal to this. Why? Because it will cancel out here, but you also have a shear component. So this is the normal component, and then you will have a shear component. Okay, so you will have a component of sigma 33 which will be acting perpendicular to this plane, and that will be sigma 33 cos theta. Okay, so sigma 33 cos theta will be perpendicular to the axis of atoms. So you see there will be extra stress working on this one, and because of that these atoms will not be pulled equally apart in comparison to the atoms if you apply the same stress in this direction and same stress in that direction. And so because of such kind of crystal structure which does not have symmetry like that one, we will have different elastic modulus, values of elastic modulus here and different there. Okay, so that was all about elastic relationship and the relationship between stress and strain energy density, and the compliance and stiffness matrix. And we will now talk about plasticity in our next lecture. Thank you.